Okay, so today is our last lecture on aromaticity, and then you'll have your exam for this module open today at 2:15, 24 hours to do that. It'll close tomorrow, and then I'll score them sometime tomorrow afternoon. You can check your zip grade for your scores. And so what we'll focus on today is applying all of these reactions that we've learned to making some di-substituted or higher substituted aromatic rings. We'll go through this first example, and then I'll show kind of the general considerations of looking at a target, and then we'll do a couple more and see how many we can get through. So the prompt here is to make metatoluidine. So again, meta is the 1-3 relationship. And again, a lot of these mono or di-substituted benzenes have common names. So toluidine is not the IUPAC name. If you're not sure of what it is, you can look in your textbook or Google the name, you'll find out. And so it wants us to start from toluene. So when we just visually look, we can see that the methyl group is already in place. So toluene provides us with that methyl group. So what is the issue of starting with toluene? The alkyl group is electron donating through induction. So by definition, electron donating group is an ortho-para director. And we need a meta relationship in the target molecule. So really what we have to do is figure out a way of blocking the 4 position, the para position, and then doing some stuff that will direct into that meta relationship. So before we even start, the methyl group is already there. We need to get an amino group on there. So one sort of thing you can do when looking at these is, okay, that's an amino group. That has to come from a nitro group through a reduction, and then I get that on through nitration. So any substituent you see on the ring, just put like a little note of how does it get there. And then what we're concerned about is the strategy of sequencing the reactions to get the proper relationship. So in the discussion here that I'll walk you through, we're going to leave the methyl group alone and proceed with the electron donating ability, and then use a blocking route that we ultimately have to deblock because that 4 position is hydrogen. So overall, H needs to go to H. And we have to block, do some stuff, and then whatever group we put on as a blocking group, we have to remove and replace it with that hydrogen. So we learned some reactions to do that, primarily through the diazotization route, where we could then quench with with H minus as a nucleophile. So I guess I'm going to start drawing downwards so that I have enough space to do stuff, and then so ortho-para director. And we're going to assume that the para is the major product due to steric hindrance. The first thing we're going to do is a nitration. So we'll treat with HNO3, fuming in the presence of sulfuric acid. So now we have this para-disubstituted benzene. Of the two groups that are on there now, if we were to run a third reaction, the nitro group is going to win in terms of its ability to direct, because it's an electron withdrawing group by resonance. Methyl is induction, so resonance will always win. So the next substituent would go there, and we don't want that. We want the meta relationship in the target. So what we're going to do is reduce that nitro group to the amino group. So we can use hydrogen gas, iron metal, HCl, and then adjust the pH so that we end up with the amino group. So that's taking nitro down to the amino. So we haven't changed the relationship. It's still para. We're not at the target because we need a 1,3 and this is a 1,4. But what we've done now is switched the reactivity, so we have an electron donating group and an electron donating group. The para position for both is blocked. It's already substituted. Methyl directs through primarily induction, so that's weaker. So it would direct here. That's the ortho position to the methyl. The amino, since it's directing through resonance, is going to direct there. So that's going to win, even though we have these conflicting positions to direct to. So we need a nitrogen now at that position. So the way we know how to get nitrogen onto the ring is through nitration, so we'll repeat that, those conditions. So at this point, the ring is tri-substituted, so the nomenclature of ortho meta para no longer applies because that's specifically for a di-substituted ring. So even though we have 3 substituents on, we're in the right direction in terms of the relationship between the methyl and then that nitrogen at the 3 position. Fortunately for us, the amino group and the nitro group are at different oxidation states. So we know conditions that will specifically target them without reacting with both. So we're going to use the fact that they're differentiated to act upon the amino group at this point. We don't want to do anything with the nitro at this time. So we can treat this with sodium nitrite. In the presence of aqueous HCl at 0 degrees. That will generate that diazonium. So it's not touching the nitro, it's just acting on the amino group. And then we can quench that with H3PO2, that hypophosphorus acid. That's going to deliver H- to that position. And what we end up with now is the meta relationship, because we're dealing with the methyl group and the nitro. So the 1-3 relationship, that's what we need. And then now we need to do a reduction of nitro to amino to end up with our target. And so for this time, we'll use tin dichloride. So it comes as a dihydrate in the presence of ethanol. So that's going to reduce down the nitro. To the amino, and then we end up with our target. Any questions on the strategy? I guess what I can point out is if we were to take the methyl group and oxidize it to a benzoic acid, which is a meta-director, that would then allow us to install the nitrogen at the 3 position. But then we still have to go through some reduction stuff to get that back to a methyl group. So no matter what strategy you use, you always have to consider the oxidation state. And typically in a synthesis strategy, we want to kind of avoid doing unnecessary oxidations and reductions because overall, in terms of producing things, it takes time and resources to do that. So maybe we can, just so I refresh your memory on things, do a little practice here about the target. And so the first question would be, what's the molecular formula of metatoluidine? So the ring is 6 carbons, the methyl makes 7. Yeah. C7H9N. So why don't you try calculating the molecular weight of that? So 107. So one thing I want to point out, we have 1 nitrogen, so an odd number of nitrogens. That's going to make your hydrogen count odd. Overall, the parent or molecular weight has to be an odd number. So whenever you have an odd number of nitrogens, the hydrogen count is going to be odd, and therefore the molecular weight will be odd. How many degrees of unsaturation are there? So there's 4. It's 1 ring plus 3 pi bonds. Given the structure, how many carbons are sp3 hybridized? So 1. How many are sp2 hybridized? 6. How many are sp? So other than the plane of the projector, does the molecule have any sort of symmetry? So in the carbon NMR of this, how many signals would you expect to see then? What? 7. So every carbon is unique, so you'd expect to see 7 signals. And the reason for doing the hybridization analysis is that you're going to see 1 signal set off by itself, sp3, and then a cluster of 6 together because they're all sp2 in the aromatic ring. So including the NH2 group, how many sets of hydrogen would you expect to see? Six. So let's further classify those 6 sets. How many sets would belong to CH3 groups? So 1. How many would belong to CH2 groups? Zero. CH groups? 4. And then we have that NH2 group. So that gives us our 6 sets, and then those are the attached hydrogens. Let me see if this will run it out of space here. Apologize because you can't do that on yours, but maybe you can. Insert a blank slide there. So I guess the next thing we can do is let's run through each of those 6 sets of hydrogen. We know what the attached, so the carbons have those specific attached hydrogens to them. And let's try to estimate what the signal would look like based on the number of neighbors. So the methyl group is a set. So the carbon has 3 attached hydrogens. If we look at the number of neighbors, how should that signal appear in the proton NMR? So that carbon has 1 carbon neighbor. How many hydrogens are attached to that? What? None. So that carbon shows 1, 2, 3, 4 bonds, so it has no hydrogens. So the signal is going to be a singlet. So a singlet that integrates or has a ratio of 3. So if we, I guess, walk around the ring, we'll do clockwise. Carbon, no hydrogens. Carbon, 1 hydrogen, so CH. How many neighbors does that have? So that has none. So that's also going to be a singlet. The next carbon has no hydrogens. We have this amine group. So hydrogens bonded to heteroatoms kind of behave uniquely based on how the sample was prepared. We have a nitrogen with two hydrogens. You may or may not see a singlet that's broad. So we can say broad singlet that integrates to two H's. And the reason it's broad is because now there's this possibility for hydrogen bonding that just takes your signal and makes it look more like a hill. So now we're down to this hydrogen here. How many neighbors does that have? So it has one. So we apply the n+1 rule. So this will be a doublet with a ratio of 1 hydrogen. We keep going, we run into this next H. How many neighbors does it have? It has 2. So this is where it gets a little fuzzy. So 2 + 1 is 3, that's a triplet. So that hydrogen, you're looking at this neighbor, that's your 2. 2 + 1 is the triplet to a first approximation. The reason that isn't the best approximation is because this last hydrogen, that one and that one are different. And because they are different, the signal may not look like a triplet. If you consider them individually, you have a neighbor here that forms a doublet, and then a neighbor there that forms a doublet. So overall, it could look like a doublet of doublets. And the reason for that is because the coupling between them could be different. If the coupling's the same, it just converges into a triplet. So the last one here, it has the one neighbor, that's going to be a doublet. And that's 1H. So if you kind of run through that exercise when looking at, a product or possible responses, when you go to interpret the data, you'll have a better idea of if it's confirming that or if it's rejecting it because something's different or there's an absence. So that we close the loop here, as they say, let's look at the meta or yeah. The NH2 group will be broad due to hydrogen bonding. So you'll have another molecule of this metatoluidine that's hydrogen bonding. And so that interaction sort of kind of stretches the NH bond. The result of that, in terms of how the signal looks, instead of like going up then down, it kind of just looks like more like a hill. They're pretty broad. So for any dye-substituted aromatic, you can have an ortho, a meta, or a para relationship. So let's do sort of the same counting and see if any of those numbers change, like the 7 and the 6. So how many unique carbons would the ortho isomer have? So the only way that like the total carbon count can be lower is you have to have some form of symmetry. So again, the like plane of the board itself, which would like slice the molecule in like half, top and bottom, that really doesn't reduce that number. It has to be kind of orthogonal. So this is still going to be 7. So if we were looking at carbon data, right now we couldn't tell. You know, if we just saw a spectrum with 7 signals, we couldn't differentiate. What about the sets of hydrogen? Does it stay the same or does it change? This one's going to be 6 as well. So right now we see, just based on the bulk numbers, nothing has changed. But let's do the same analysis of the neighboring thing and see if anything else is now different. The methyl group, nothing changes there. That's still going to be a singlet. The 3 H's, so no differentiating. The NH2 will still be a broad singlet, 2 H's. Now if we're into the ring, that H should be what? So that'll be a doublet. The next H, so triplet. The H next to that, triplet. And then the final H will be a doublet. So even though the 7, 6, and 7, 6 are the same, when we look at the neighbors, we can see that of those 6 numbers, this has singlet, doublet, triplet, doublet. This now has doublet, triplet, triplet, doublet. So we can look at the patterns to confirm what the relationship is of the 2 substituents. So the last one was the para. How many unique type of carbon will this have? So this will have 5. So now that we've taken the symmetry plane and now it's orthogonal to the plane of this board. So the mirror plane is here. And in doing so, that's a unique carbon. So we start our count as 1. That's unique, so that's 1. But then when we branch off, those two are the same type. So we don't count them differently now. These two are then the same type. This one is different from that one, because that has methyl, this has amine. So overall, we can reduce from the total count of 7 down to 5. So if you saw carbon NMR data that only showed 5, you would say it has to be the para because the other two are going to have 7. And then the total hydrogen set count should be so that'll be 4. The signatures for the methyl and the amino won't change. So singlet 3H, broad singlet 2H. So maybe I'll draw these kind of different. So that's a set. And then that's a set. So 2 sets of 2. Each one is going to occur as a doublet. So the proton NMR will look unique for all of them, based on the neighboring, looking at the neighboring hydrogens, how does that affect the signal multiplicity? So we've differentiated the meta and the ortho based on that analysis. And then the para one is only going to have those 2 unique signals in the aromatic region. Questions? So I'll run through some strategies, some considerations, and then we'll use the rest of the time to solve some problems. So first things first, if you're given a name, always draw out the structure. And as I said, a lot of these have common names, so you can look in your textbook to find what that structure is, or just Google it. You'll find it that way. Once you have the structure drawn out, for every substituent that's on there, classify it as electron donating, which is then orthopara, or electron withdrawing, which is meta. The next step is, once you've identified what that substituent is, go back and review the reaction conditions to get it on there. So once you have those notes down, what is the relationship of all of those substituents relative to one another? And once you have all that information, all you're really doing is sequencing them to get that proper relationship. Because sometimes it does matter if you do this step before that step, it's going to switch how those things end up on the ring. So a couple of notes, observations from the stuff that we've learned. Benzene itself is our benchmark for reactivity. So if we benchmark that as 1, a substituent that's an electron donating group will always react faster than benzene. And again, that's important when you have a molecule with more than one benzene ring. On what ring is the reaction going to occur first? So on the opposite end of the spectrum there, the withdrawing groups react slower. So you might be able to take advantage of that. So Friedel-Crafts alkylation, that installs a carbon that's at oxidation state 0, an alkyl group, and those are ortho-para-directors by induction. And so remember that resonance is a greater influence on direction than induction is. So even if you have that alkyl group, if it has a CH, you can oxidize it to a benzoic acid, which then flips the reactivity to a metadirector. The opposite strategy of that is called acylation. That's going to make a ketone, which is an electron withdrawing group. That's a metadirector. We can reduce that ketone with the Clemmensen reduction, and that will flip its reactivity to an electron donating group, so an ortho-para-director. And then depending on the nature of the side chain, if it's linear, then we need to use the acylation reduction. If it's branching at the benzylic position, then it's coming from an alkylation. So the nitration was pretty versatile. It installs an NO2 group, which is an electron withdrawing group or a metadirector. We can then flip its reactivity through a reduction that forms the amine group. And now that's an electron donating or ortho-para-director. So we can either use the amine in terms of directing, or we can transform that through the diazotization reaction, also called the Sandemeyer reactions, which will allow us to install oxygen to make a phenol, or we can make ethers from that. We can displace it with cyanide. So that's the nitrile. And then we can access the other halogens, fluorine or iodine, or if we need to, we can use chlorine or bromine at that point. So those are the tools that we can use. Here's a list of compounds you can practice on. We'll go through hopefully 2 or 3 of them, just to give you an idea of the ordering of things. But as it says up there, one thing you want to consider as you design your sequence. I mean, you can do it from just what you see here. Just draw those out in terms of the structure, and then try to think of the unique carbons, unique hydrogens that you'd expect to see in the product. So our first one is para-bromobenzoic acid. In terms of the conversion of the name to the structure, again, para is the 1,4. The way these things are named, the highest oxidation state functional group gets the parent. That 3 is saying that the acid is at oxidation state 3, so that's why it's named as a benzoic acid derivative. And then obviously the bromine is the other substituent. So when we look at the target, what do you think we should start with? So we see the aromatic ring coming off at the 4 position is bromine. At the top, I'm going to put a blue dot, that's a carbon. So in terms of starting, if we had to choose between benzene or toluene, toluene would be the better choice because it has that carbon already on the ring. Now, the carbon in toluene is at an oxidation state of 0. So we have to do something to it to transform it ultimately. But if we start with toluene, at least we have that carbon. We don't have to add extra steps to get it on there. We know that the alkyl group, methyl, is an ortho-para director. And we only have the one other substituent, which is bromine. So we can get that on there with bromine and iron tribromide. So there's the ortho and para positions. I drew the para arrow longer because we're going to assume that is the major isomer that comes out of this. So now we have the right relationship we need. The only remaining stuff is to change the oxidation state. And because this carbon that we started with of toluene, because it has a hydrogen, remember the minimum requirement is 1 hydrogen. What we can do is that benzylic oxidation. So sodium dichromate, and I forget what other stuff's in there. But that's going to go from 0 up to oxidation state 3. It doesn't change the positional relationship. All it is affecting is the oxidation state. So now we started at 0, and now we're ending at 3, and there's our target. So just to point out some things to look for in terms of the structure, the molecular formula that can clue us in. The formula is C7H5BrO2. And of the 7, we would see 5 unique carbons. All of those carbons are sp2 hybridized, but one of them is different because it belongs to the acid, so it's a carbonyl carbon. So in the carbon NMR, you're going to see one sort of signal set off by itself and then a cluster of 4. So because of that, we know they're part of different functional groups. The presence of the bromine, there's one bromine. So in the mass spec, the parent, you're going to see an M and an M+2 in a 1-to-1 ratio. So you're looking at, sort of the right side of the mass spec. The parent ion has essentially the molecular weight. That would be your M. Then you're going to see another signal, M+2, and the intensities will be 1-to-1. So overall, we have 5 degrees of unsaturation. 4 belong to the ring. 1 belongs to the acid. And so in the infrared, you're going to see the carbonyl CO double bond stretch, and then you're going to also see the OH stretch. So those things are pretty unique. So the IR is going to tell you, yes, there's an acid. Mass spec tells you, yes, there's a bromine. Then the carbon and hydrogen spectra tell you essentially what the substitution pattern is, that it will have to be para. Any questions? So this one says metabromobenzoic acid. So now the two substituents are in a 1-3 relationship. We can still use the same logic as before, where we'll start with toluene. So we're doing the exact same reactions, but now we're going to run them in a different order. So instead of doing the bromination first, we're going to do the oxidation first. So we oxidize methyl up to the benzoic acid. That now gives us the right oxidation state. What it also does is flip the reactivity. So now this is a meta director. So it has to go there. And then we do the bromination. And we end up with that 1-3. So between the prior example and this one, the IR is still going to have this signature for the carboxylic acid, so you really couldn't differentiate them that way. The mass spec will still have the same parent, and then parent plus 2, so that won't differentiate them. What you'd have to look to now is the carbon NMR and the proton NMR. Those signatures would be different. So I would say, generally speaking, when you're dealing with a dye-substituted aromatic, as long as you identify what the substituents are, backtrack to how you get it on there, really you're just dealing with sequencing them. When you get into these situations when there's like 3 or more substituents on the ring, then it gets a little bit more challenging, because you have to analyze how each substituent is going to direct, and then relative to each other, which one's the most powerful. And then do those positions where they direct reinforce, or are they directing to different positions, and then how do we solve that? So that's when you also have to think about blocking. So block a position and then remove it later. So let's, we'll wind down with this last one here. 2-bromo, 4-nitro aniline. So aniline was aminobenzene. In terms of the ring numbering, that's going to be position 1. And then it says at the 2 position is bromo, and at the 4 position is nitro. So for either of these N groups, we get those on there through nitration. They're at different oxidation states, so one of them has to be reduced To get bromine on, we do bromination. So now those are the reactions. We just have to move the pieces around to get the sequence right. I'm going to kind of rig the discussion here. We're going to start with nitration. Alternatively, we could have started with bromination, but that's bromine versus nitro. The ability to direct, nitro is much greater. So we want to start with the thing that's going to give us the most versatility while also kind of ruling out the possibility to form any isomers we don't want. So for this, we do have to start with benzene. We don't have any carbons attached to the ring, so there's no point in starting with toluene unless you like making life painful and trying to remove a carbon from a ring, which is not something that's easy to do. So let's start with the nitration. And so I'm going to put it there. And I promise I'm not doing anything weird. So I drew the nitro group up there, even though on the target it's drawn on the bottom. So nitro is a meta director, right? So if we were to run another reaction to get a substituent on there, it's going to direct there. And we can see we don't want that. So at this point, we'll reduce it. So we'll use the tin dichloride in ethanol. So that takes nitro to amino. And so that was aniline. And again, this is all just paper chemistry. We could probably just buy aniline rather than making it. So we've now flipped the reactivity. This is an ortho-para director. So tiny arrows for ortho, bigger arrow for para. So we know para to that amino group is the nitro, so now we'll do a nitration. We'll assume that the para isomer is the major. So amino is ortho-para directing, nitro is meta directing. Maybe I'll do this in different colors for my own gratification. So ortho-para in blue. The para position's blocked. So meta in green. So meta relative to that nitro group. So now those two substituents reinforce one another. And that's exactly where we need that bromine, so we don't have to do any weird blocking or anything like that. So we can just finish off with the bromination. So aside from any like minor isomers being produced from an ortho-para distribution, there really isn't any major flaws in terms of the positions that we'll end up with here. Like I said, if we tried to run through this by starting with just a bromination, if we did that first, I think there would be a lot more issues controlling the total number of isomers that are produced, because things wouldn't reinforce as well. So one thing I will point out, so every carbon in there is going to be unique. There's no perpendicular plane of symmetry. Because there's an even number of nitrogens, the parent mass should end up being even. So you probably can't tell by looking at the mass spectrum, the presence of the nitrogen atoms. The bromine is still going to show that 1-to-1 ratio. So what makes this one a little bit more difficult, the NO2 group doesn't have some prominent signatures that we've seen in IR to tell you, okay, it's NO2. So there's some information you just have to infer from the proton based on how that group affects the chemical shift of the protons on the ring. Since it's really strongly electron withdrawing, they're usually separated from the normal cluster. Like when you see something that's around 6 or something that's above 8, then you can say, okay, that group is really affecting where these things fall on the ring. Any questions? So that's pretty much all that I wanted to go through. Again, your exam 2 will open up on about 6 or 7 minutes here. I'd say pay attention to the data. Some questions are pretty straightforward, like falling off the chair and let gravity doing the work. But other ones, look at the data and what is the specific thing it's telling you. You should then be able to rule out all the derailer answers. Other than that, like I said, you have 24 hours to do it. I'll have it graded by about 3:30 tomorrow. Then you can go into ZipGrade and check out your scores. Other than that, we're done.